Okay, good morning. Let's start with SAT. So, there's a lot of these people that work on practical SAT solving problems and they claim they're good at it. So, somebody might come along to you and say like, hey, I can solve SAT. Like, here's the circuit that solves SAT. And, you would be like, I don't know if I believe you. But perhaps you're like a practically minded person, like really you don't care that much if they're right or wrong. You don't want to necessarily refute or confirm their claim. You just want to solve SAT. Like you just have some particular phi, and you're like, man, I really wish I knew whether this guy was satisfiable or not. So what can you do? Well, you can plug it into their circuit that they gave you, and maybe it'll come back and say yes, i.e. it is satisfiable. Of course, that's a little suspicious, but SAT has a great property, which is that it's downward self-reducible. We've mentioned this several times, or sort of equivalently, that has like search to decision reduction. So you fix x1 to be 0 or 1 and ask again, like, is this one SAT, or so forth. And you can keep doing that. And one of two things will happen. Either you'll detect a bug in this code C, like maybe it'll give you some inconsistent answers, like it says phi is SAT, but then you try setting x5 to 0 and to 1, and in both cases it says unsat, in which case you can just, go back to them and say, like, C is bogus. Or you'll get a satisfying assignment. And then you don't have to worry about whether or not you trust C or whatever. You don't know what it did, but like it came up with a satisfying assignment, so great, phi really is satisfiable. So that's a great property of SAT. It has this downward self-reduction property. The downside is like, well, it's not so great, because what if it comes back and says, no, this is not satisfiable? Well, I don't know. What are you going to do? I mean, you can cross your fingers that C is correct, but maybe you're not so sure. The good thing is, though, this is better than nothing. This is very useful. In fact, we use this heavily in the proof of Karp-Lipton. Remember, the Karp-Lipton theorem from 82 says that like if SAT is in P/Poly, or if NP is in P/Poly, then that implies the polynomial time hierarchy collapses to sigma 2p. Intersect pi 2p if you like. Okay, and if you kind of remember the proof, you kind of guessed a potential circuit for SAT, and then you're not sure. You're kind of in this situation where you're not really sure if it works. But this aspect helped you. I mean, it helped you that like when something was satisfiable, you could extract a witness out of this potentially questionable C. Okay, so in this lecture, we're going to see a similar thing, but like with permanent instead of SAT. And permanent has arguably even more like great properties than SAT. It's not only downward self-reducible, it's also randomly self-reducible. And that'll make things even better. But before we get there, I just want to say a little bit more in the world of SAT, because it'll give us some motivation. By the way, if you remember on your homework, like you got, I think it was on homework, you got an even stronger collapse to this like highly bizarro class called S2P. It was just called S on the homework. This is like a subset of this class, and so therefore it's technically a stronger result. Yeah, so one motivation, but like one cool thing you can use Karp-Lipton for is the task of proving circuit lower bounds for ideally small complexity classes. So there's this theorem we did in lecture 8 due to Kanan, where we just explicitly constructed a language that was in sigma 4p, which was not in like size n to the 100. Okay, you can actually put any fixed number here, but I'll just say 100 to keep the notation short. And we did this just by considering like the language of like all the strings that are like the lexicographically least circuit that basically don't have this size, and we argued that it was in sigma 4. And that was cool. We found a language in not too high a complexity class that provably didn't have circuits of size n to the 100. And then as a little bonus, we had this like kind of hilarious corollary to it, where we actually like improved this sigma 4p down to sigma 2p, which was great. And I'll just remind you of that proof. So the proof of this was like one line long. It went like this. So you know this fact. You're trying to prove that sigma 2p is also not in size n to the 100. So you just say, OK, look, if sigma 2p doesn't have polynomial circuits of any size, then of course you're done. You're way better than done. I mean, great. On the other hand, if it's not in p/poly, you're totally done. On the other hand, what happens if sigma 2p is in p/poly? Well, I mean, SAT is in sigma 2p. I mean, it's in NP, so it's even better. Then SAT would be in p/poly. And what happens? Karp-Lipton then tells us that pH equals sigma 2p. OK, so the whole hierarchy collapses down to sigma 2p. And certainly, like sigma 4p is like sitting between these two classes. So everything is the same. And then you're done again, because Kanan told you that this thing is not in in size n to the 100. But under this assumption, sigma 2p is sigma 4p. So you're done. And this is like a good motivation for like trying to improve Karp-Lipton. So you see, you can just do the exact same proof with S2p and get the also this bizarre class S2p does not have size 100 circuit, n to the 100 circuits. Because you just repeat the exact same proof, but you just get this down to like S2p here. Not that I'm obsessing overly about this weird class S2p, but it's kind of a motivation for getting strong versions of Karp-Lipton, because like the smaller the complexity class you collapse to down here, the better conclusion you can get of this sort of circuit lower bound form. OK, so we're going to see that phenomenon today. All right, so let's, as I said, start to repeat the same story, but with the permanent. OK, so let's say some person comes along to you and says, hey, I know a great algorithm or circuit for computing the permanent. And again, you're like, that's very suspicious. Like, I don't really believe it, because I don't actually think there is a small circuit for computing the permanent. But, well, let's see. Yeah?
So kind of construct a language that you can show doesn't have circuits. Mm-hmm. Is there a language in sigma 2p that you can sort of construct?
That's a good question.
To basically make this proof constructive.
That's a good question. This proof is constructive in the sense that you explicitly give the language. You explicitly give a sigma 4 Turing machine, and the language of that machine doesn't have polynomial size circuits. This proof is non-constructive, though, because you don't actually know which case you're in. I mentioned this on Piazza, actually. A subsequent paper of Tsai and Watanabe made this result constructive. They actually explicitly gave a sigma 2 machine. But this one, we don't know how to make constructive. This one we only know how to do with this funny proof. OK, so I want to imagine this scenario, but there's two cases that I want to talk about, and each case will occupy us for, I don't know, 20 minutes. And the cases are just whether here I mean C is an algebraic circuit or like a normal Boolean and or not circuit. So let's start with the case where it's an algebraic circuit. Okay. And for a little simplicity, let me imagine that it's a circuit with plus, minus, and times gates and no division gates, because we can actually get rid of them. And let me also assume it's over the integers. That's with loss of generality, but whatever. Let's say they were like, hey, it's even a circuit that only uses integer constants. And even further, let's imagine that these integer constants can be expressible with polynomially many bits. I mean, we're kind of imagining the scenario where a person literally hands you a description of the circuit. So, the numbers should not be too crazy. So let's imagine again what to do if you're skeptical about this supposed algebraic circuit that is of polynomial size and supposedly computing the permanent. And let's again use the fact that permanent is downward self-reducible. Okay, that's one of the very first nice properties of the permanent that we mentioned when we introduced it. And let's look a little bit more carefully about what that means. So basically it means this. I mean, if you have some n by n matrix, I call it X, There's this like cofactor way to like compute the determinant where like the permanent, like you go across the top row, like for each entry you like cross out the top row and that column, and you imagine inductively computing the permanent of the remaining matrix, and you multiply it by the number and you add it up. So in other words, this is a formula for the permanent. Okay, where xi, I mean the matrix you get by cross out the first row and ith column of x. Okay, that's one way to compute the permanent. You see it reduces computing n by n permanents to n minus 1 by n minus 1 permanents. And let me label this equality or identity with the label ID n. It's some identity, and the n refers to the fact that it's reducing n by n permanent to one lower size permanent. Okay, and I won't write it, but let me also introduce, like ID n minus 1, which is what you would get if you just did the same statement about reducing n minus 1 size permanents to n minus 2 size permanents. And you can keep going to ID 2 about reducing size 2 permanents to size 1 permanents. And, well, like ID 1, I'll just say is just the fact that the permanent of a 1 by 1 matrix X is just X. And what I want to say is the collection of all of these polynomial identities is like defining for the permanent. Okay, I mean, if you have like some matrix function that satisfies all these n identities, then it's the permanent. I mean, it's just the definition of the permanent in some sense. So in particular, if C, this supposed permanent computing algebraic circuit that this shady character gave to you, if it satisfies all of, ID 1 up to ID n, then, and indeed it's computing a permanent. Okay. Now, there's something a little bit annoying about this minor technicality, which is that it doesn't quite make sense to ask if C satisfies all these things, because, they gave you a circuit C for n by n permanent, and, even ID n asks you to say, imagine plugging in n minus 1 by n minus 1 matrices into C. And, formally, you can't really do that. It's actually the same problem if somebody hands you a circuit for SAT on n variables, and you want to do downward self-reduction. You get SAT formulas on n minus 1 variables. So, it's slightly annoying if you only have an n variable SAT solver, but it's just a technicality we can get around. So what we'll say, just so that this makes sense, is let's say you have a matrix A that's k by k. I'm just going to define, quote unquote C of A to be this. C applied to the matrix A in stuck in a block diagonal matrix where this A is k by k, and this identity matrix is n minus k by n minus k. Okay, so if I want to use C to find out what does C think the permanent of A is, I'll just say I'll get my answers by doing this. And if C really is computing the permanent, then that's fine, right? The actual permanent of this matrix is the same as permanent of A. So if you do this cofactor expansion starting from here, it's just 1, and then you cross everything out, and 1, 1, 1, 1, 1, and you just get the permanent of A. Yep?
So that's just to blow up the A, so that will give the matrix size of n by n.
Yeah, because this is a bit of a technicality, but we're just assuming that somebody gives you a circuit that takes in exactly n squared variables and claims to compute permanent on n by n matrices. But we kind of want to, analyze it on smaller matrices too. And Right. So we're just going to use this technique for like asking C about what it thinks permanents of smaller matrices are. And this is like a valid thing to do in case that C is correct. And conversely, if C is incorrect about some, like in this sense, about some small matrix A, then it's incorrect about some n by n matrix, this blow-up version. OK, so that's a little technicality. OK, so now I want to make the following observation, which is that each of these identities is an instance of the so-called polynomial identity testing problem, which is a problem we talked about in lecture 5 in the context of randomness. Okay, if you recall, the polynomial identity testing problem, PIT, is you're given two algebraic circuits with like plus minus times over Z. We mentioned these objects back in lecture 5, actually. And you want to check whether or not they're computing identical polynomials. And that's what's going on here, right? If you imagine putting C in here. I mean, to ask whether C satisfies this is whether this circuit, C, is identical to like this circuit, which you can build yourself, right? I mean, you use C here, well, in this way. And then, add a few more times and plus gates and form this circuit yourself. And to then ask whether this identity is true about C is asking whether two algebraic circuits that you have your hands on are identical. And similarly, you can build all the circuits yourself for these other identities. Yes?
Does it make a difference whether PID is defined in terms of formal other circuits?
I guess technically, yeah.
But are they like equivalent to TPP or?
So I mean, if you have a polynomial identity testing problem about circuits and you want to reduce it to one about formulas, I don't quite know how you can do it, except by the generic trick of blowing up a circuit to a formula where you pay log of degree in the exponent. Generically, though, if you just have a circuit of size, we're going to use this fact. If you have a circuit of size m, the degree of the polynomial computes could be as large as 2 to the m. So I'm not sure you can sort of generically get down to formulas. So as we mentioned back in lecture 5, I mean, I brought up this precise problem because it's actually basically the one problem we know can be solved in BPP or co-RP, but we don't definitely know how to solve in P, even though we overall believe that BPP equals P. And I'll say recall, although I'll also remind you how it works. This is from lecture 5, and it's also in the textbook, chapter 7.2.3. This problem, PIT, is in co-RP. Okay, so you can solve it efficiently with a little bit of randomness. Well, polynomial amount of randomness. The proof of this uses the so-called Schwartz-Zippel lemma, which is not hard to prove and basically says that, if two polynomials like agree on enough points, they have to actually be identical polynomials. Okay, it's like a generalization of the fact that, if two univariate n-degree polynomials agree on n plus 1 points, they have to actually be agreeing on every point. They have to be the same. So more precisely, this lemma says, which again, I didn't prove, but you can read the simple proof here. If degree d, and these are multivariate polynomials, p and q, agree on random inputs from the set, you plug in for each of the variables, let's say n variable polynomials. You plug in for each variable a random integer between 1 and m. If they agree with high probability, at least d over m, then they're actually equal as formal polynomials. Okay, and so therefore, what is the idea behind the proof that polynomial identity testing can be solved in co-RP? Well, it's a very intense M. The high level is you have these two circuits, and you pick a random input for both of them, where like each number is between 1 and m, where m is like a very big number, which I'll come back to. And then you see if they compute the same number. And if they don't, they're definitely unequal. And if they do, you're like, well, they're probably equal. And the degree of these circuits is at most exponential in their size. Because the fastest way to blow up degree is just have tons of times gates. But still, the degree of a circuit will be at most an algebraic circuit exponential in its size. And that's OK. So I mean, you can just take m to be like bigger than that, like an even bigger number of the form exponential in poly, which has polynomially many bits. So you can write it down. And then there's one more trick, which is you have to like try to compute the circuit. When you plug in these potentially very big numbers with poly-n bits, and actually, if you did it exactly, the bits could get to be exponentially many. But you do it modulo like a larger number, and the error is still fine. And so I won't go into too more details than that, but it's basically you just plug in random inputs and see if they're the same or not. But crucially, this is like a cool conclusion. Like if they agree on enough random inputs, then they have to be identical. And that uses the fact that they're both computing polynomials, and polynomials are sort of rigid objects. So it makes some sense? So what's cool now is that if you are you're always like a poor polynomial time potentially randomized algorithm. You can check all the IDs, all the identities, in polynomial time in co-RP. OK, well, there's n of them, but just boost your error probability so it's much smaller than 1 over n, and then just check all of them. And what that means is, you can decide, with high probability, if C is correct. I'll give an exclamation mark there. And this is a polynomial time algorithm. OK, so suffice it to say, if somebody gives you an algebraic circuit that they, polynomial size that they claim computes the permanent, then you can check that claim in polynomial time with randomness. That's cool. And this is a nice fact, and we're actually going to use it later in the course. So a later corollary that will derive from precisely this fact is that if derandomization holds, so if BPP is equal to P, this becomes a deterministic algorithm in that case, then you can get circuit lower bounds for nexp. Well, let me just say, then circuit lower bounds and I could prove that to you. Now that we know this fact, I could prove this to you in like 10 minutes, but I won't because it's a little bit unmotivated at this point of time. Like, OK, if you can always derandomize, then you get circuit lower bounds for nexp. Let me just say, why is this particularly interesting? It's because also later, when we study derandomization and the philosophy of hardness versus randomness, the main thing that you show there is that the converse is true. So the main result about derandomization we know, which comes from this like hardness versus randomness paradigm, is that if you can show that there's a language in nexp that doesn't have polynomial sized circuits, or maybe even better, like doesn't have sub-exponential sized circuits, which is pretty believable. I mean, we kind of think that like I don't even think that like SAT doesn't have polynomial sized circuits. That's definitely an nexp. Then you can derive as a conclusion that BPP equals P if the circuit lower bounds are strong enough. OK, and that's basically the main reason we believe that BPP equals P. So that was proved in like the late 90s. And then actually, it's maybe unclear why it took this long, but like later, it was shown that basically the converse holds. That on the other hand, if you manage to show BPP equals P, then it follows by necessity that you must have circuit lower bounds for nexp. And those views kind of cool. It's like, it's like an equivalence relation between the problem of showing derandomization and the problem of showing circuit lower bounds. Okay, and this corollary is like not too hard to prove from this fact. But you'll just have to take my word for it. We'll see it later. Okay, any questions? Okay, so that's the scenario when C, this purported circuit for solving the permanent, is an algebraic circuit. And now I'm going to move on to case 2, when somebody gives you, a Boolean circuit that they claim solves the permanent problem. And this is, with and, or, and not over bits. And again, there's like a little bit of like a technicality in terms of like what I mean here. So let me fix what I mean here. Looks a little specific, but let's fix it like this. Let's imagine they give you a circuit with like a bunch of inputs. And let's say it takes like, an n by n matrix of, what do I choose here? N squared bit integers. Okay, so let's say it has like, I guess like n to the fourth like input wires encoding n squared bit integers, the forming a matrix. Okay, and then the answer will be about n cubed bits of permanent. So let's say it has here some order n cubed bits in the output. Okay, so let's imagine that somebody hands you a circuit that looks like this. You can imagine it's of polynomial size, and they say, oh, believe me, this computes the permanent on n by n matrices with entries that are n squared bit integers. And again, your response will be, that does not sound very plausible. But maybe, I can, check, confirm, or deny this. Well, the first thing you're going to ask is like, well, I mean, it's just a slightly different model. Can I do the same trick? And you can write this all down, but now you're deciding on an identity between two Boolean circuits. And there's a contrast here between that and polynomial identity testing. If I give you two Boolean circuits and I ask, do these compute the same function? That's a hard problem. That's co-NP complete. It's the same as asking if their XOR always computes 0. In other words, is the XOR of the two circuits unsatisfiable? So it's basically unsat. So that's a much harder problem, and we can't expect that we just solve it in co-RP. So that's kind of a drag. But all is not totally lost. You could still basically do the same thing and see what you get. I mean, see how you feel about it. So you could just try to verify ID1 by just like plugging in tons of inputs and checking that it always works. Verify ID2. Like once you become confident that ID1 is like mostly true, check ID2 by plugging in tons of inputs and checking that it always seems to work. And thereby become convinced that ID2 is like mostly true, at least for like a random input. And keep doing it for like all the n identities. And roughly speaking, if you do that, one of two things will happen. You'll either find like a bug, and then you'll say like, sorry, you gave me a bad circuit. Or you'll basically become convinced that maybe C does not correctly compute the permanent on every input, but it at least computes the permanence on almost all inputs, like with high probability on a randomly chosen input. So let me make that a bit more precise. Not much more precise than though. So let's say somebody hands you this circuit, and I'm not going to tell you like a little, thing you can do. Again, imagining that you're like a polynomial time randomized algorithm. So step 0 will just be like find a big prime number, because we always, first of all, we want to imagine plugging in random matrices here, and it's not like a natural distribution on random integer matrices, but if you work mod p, there's like a natural random distribution on numbers mod p, the uniform distribution. So we're just going to find like an n squared bit prime, which we can do with high probability in polynomial time just by picking random n squared bit numbers and checking if they're prime deterministically. And then basically just do what I said. So for k equals 1 up to n, pick some poly n, I don't know, like n cubed or n to the 10 or something, random matrices in, let's say, z mod p to the k by k. Okay, so pick uniformly random k by k matrices over the field z mod p. And just check the kth identity on all of them. I mean, for C. And if you ever get a contradiction to the identity, then if you're done, if you get such a contradiction, output C is bogus if you find a mistake. But on the other hand, what happens if you do this like n to the 10 times and the identity checks out like every single time? Well, you basically become confident that C works correctly on a randomly chosen matrix. One small thing to observe is that if you take a uniformly random n by n matrix and focus on a particular n minus 1 by n minus 1 minor, that minor itself is also uniformly randomly distributed. Okay, they're not independent across the identity, but that's okay. So in other words, let's say you're trying to check whether the 10th identity is correct. After sort of becoming satisfied that C works correctly on 9 by 9 matrices with high probability. So when you're checking the 10th identity, you're picking a random matrix here, which is 10 by 10, getting 10 9 by 9 matrices. But you've already convinced yourself that C is almost perfect on 9 by 9 matrices. So in that way, you can kind of convince yourself that it's, or disconvince yourself that it's almost perfect on 10 by 10 matrices. So else you become confident that, as I said, C is correct. Well, at least correct mod p. You're really only checking if C is doing a good job of computing the permanent mod p, but that's good enough. On, let's say, almost inputs, I mean, I made this up, almost all inputs, at least 1 minus 1 over n cubed fraction of k by k matrices. Don't get too excited about what fraction I put here. I just, if you pick I don't know, slightly more than n cubed matrices here, then if they all turn out correct, then you've basically shown that with high probability C is right on 1 minus 1 over n cubed fraction of matrices. Okay, and let's big enough to also union bound over all choices for k. And so in the end, what happens in the end? You either catch C in a lie, find out that C is bogus, it makes some mistake, or you become convinced that it's actually working mod p on almost all inputs. So at the end, yeah, you become convinced that C is working on almost all matrices. And you can actually also kind of recognize the difference between the algebraic circuit case and the Boolean circuit case here. In the algebraic circuit case, you also can imagine you're doing the same thing, and at the end becoming convinced that the circuit works, the algebraic circuit works on almost all inputs. But then you can just instantly boost that conclusion to that it works on all inputs, because you can know that it's computing a low degree polynomial. Low is at most exponential in the size, so at most exponential in poly n, but that's still low enough because you can get your confidence really high. So just by this formal aspect to it, that you literally see you're talking about a polynomial, as soon as you know that it's doing the right thing on most inputs, it automatically, by rigidity of polynomials, gets boosted to working on all inputs. But if it's a Boolean circuit, there's no algebraic structure, who knows what ands, ors, and nots is doing, so you really cannot derive any further conclusion once you know it's working on almost all inputs. But in the case of, and you could get to the same situation for a SAT too, but what good is it really for you to know that you have a circuit that works on SAT for almost all inputs? It's okay, but if you now want to figure out the answer to your particular favorite input, phi, maybe that's one of the ones where the circuit is making a mistake. But permanent has like another cool property. It's randomly self-reducible, which maybe you remember from 2 lectures ago. Now, once you get into this state of affairs where you believe that C is working on almost all inputs, you can compute the permanent of a matrix A, again, mod P, for any worst case A of your choice. This is important. With high probability by the random self-reducibility property of permanence. I'll remind you of this in words. Remember, we said, imagine you have a circuit that computes permanent with probability at least 1 minus 1 over 3n, if you recall, mod p. Then you can compute it in the worst case for all inputs by this interpolation trick, right? Instead of just like directly plugging A into C, you're like, whoa, I'm going to do something different. I'm going to plug in like A plus x times like a random matrix B for like n plus 1 different values of x. And those are all random matrices. So if the circuit works on almost all matrices, with high probability it'll work on all of these A plus x times B's. And then you get the value of this univariate polynomial in x on like n plus 1 values, and then you interpolate and plug in 0, and you get the value for A. So perhaps you remember that from 2 lectures ago. But like there's a little trick that since the permanent is a low degree polynomial, you can get its value on one point by knowing its value on n plus 1 random, albeit not independent, other points, and interpolating. Okay? And so, again, this is important. Once you get confident that C works on almost all inputs, you can evaluate it with confidence on any input, not just the ones where it works correctly. And you don't just plug A into C, you do this interpolation trick. Does that make sense? Good. So that's pretty good, actually. We did not get into such a great situation as in the algebraic circuit case. In the algebraic circuit case, we got into this situation where we just decided with high probability whether the circuit was working correctly on all inputs or not. Now we can learn, first of all, that it works correctly on most inputs. But second of all, we can use that to compute the correct value on any input of our choice with high probability. Okay, so what we just got here is called an instance checker for the permanent. And this is actually a relatively important concept in complexity theory, which I'll now define. We got an instance checker for permanent. Okay, again, like mod a prime. So what is an instance checker? Well, it's basically what we did. So an instance checker for a function f or a language. Actually, people more usually talk about an instance checker for a language. I set it for a function because we're talking about permanent right now, but maybe eventually we'll mostly talk about languages. Anyway, a language is nothing more than a 0-1 valued function, so it's a special case. An instance checker for a particular function, like permanent, it's a randomized polynomial time algorithm. Okay, in the particular case of permanent, it's like this whole algorithm I described there, starting with 0 and ending with this. Taking, let's say, oracle C, purportedly computing f, and it also takes an input. Such that, and now I'll list its properties on the next board. The idea of an instance checker, while I erase, or sometimes called program checker, is that, again, you're in this situation where you have a circuit that supposedly computes a function, and you really want to compute that function on a particular input, and hopefully you can do it even like with this buggy program. Either you can do it, or you can identify a bug in the program. One of those two things. So what are the three properties? One, so the algorithm A with oracle C and input X, it outputs two things. It either outputs an answer, or it outputs the phrase, C is bogus. And by bogus, the intention is that like C does not literally compute F correctly on all inputs. Okay, and there are two, kind of main cases. If C is actually correct, so let's say C actually indeed does compute F. Then the property is that A outputs the correct answer with probability 1. Okay, you kind of saw we had that in the permanent, right? Like if you really literally did have a circuit that correctly computed permanent, then all your checks would pass and you would, not identify any bug and you just output the right answer. On the other hand, and this is the slightly subtler condition, if C is actually bogus in the sense that it literally does not compute F, then the condition is that A with oracle C on X is, let's say, correct with high probability, probability at least 2/3. And what does correct mean? Correct means either it outputs the correct answer, or it outputs C as bogus. Which, is correct in case 3. Okay, so either it, comes to the right answer, or it, detects a bug in the program C. This notion of a program checker was actually invented in the mid to late 80s by Manuel Blum and his graduate students. They're thinking about the problem of the exact problem, how can you maybe write some complicated piece of code that's supposed to do something. How can you check that it works correctly? And you want to actually have some kind of checking routine that's less complicated than the code itself. Maybe you implement some very sophisticated matrix multiplication algorithm that somehow works in time n to the 2.8, but the code is very complicated. So how can you really check that you did it correctly? Well, you could test it on a bunch of inputs by comparing its results against the naive implementation, which takes n cubed time. But that sort of defeats the point. You just spend n cubed time to check something that's running in n to the 2.8 time. So he was trying to figure out how can we imagine a meaning for checking the correctness of a program where the checker is much more efficient than potentially the program itself. And that's not clear, but this is a slightly different notion of checking where either you find out that it has a bug or you get the job done. Maybe you still don't know if it has a bug or not, but still got your answer. And let me just also amplify a little on this point, right? This has to be, this case is the case you're in, even if C is correct on every single input except for one input. So imagine if you have your C is correct on every single input except for one input, and let's imagine that input is not X. Then that's why you kind of have to allow this case. The checking algorithm is never going to identify that one crazy input where C fails. But that's OK. In that case, if it's wrong on one crazy input that the algorithm could never find, then you'll get the right answer. On the other hand, if that one answer or one input where C differs from F is the X that the checker actually cares about, the checker has to do something. And that's where you kind of see that something like random self-reduction needs to be in place, where the checking algorithm can evaluate the function on an input by actually asking about other inputs. Yeah.
So it's allowed to output the wrong answer with the rest of the probability, a release one probability?
Yeah. So with high probability, in this case, with probably at least 2/3, it outputs either the answer or bogus. And with the rest of the probability, it can output a wrong answer for f of x. But you can also boost this, to make this, 99.99%.
And that can happen. Everything checks out, but the algorithm is still wrong, right?
Yeah. You can also relax this to 1 minus small if you want. But since all our program checkers achieve this with perfect completeness, we just leave it there. So in other words, if your algorithm outputs the phrase, if your checker outputs the phrase C is bogus, Actually, our checkers also have the property that when it outputs C as bogus, it's definitely bogus. Although I suppose, according to the definition, we merely know that. Oh, no. Actually, if it outputs C as bogus, you know for sure it is bogus. Because if it were perfect, we have the condition that it never outputs bogus. So if your program checker outputs like C is bogus, then you definitely have found a bug. And if your program checker outputs like an answer, like 17 in the case of permanent, you know that with 99% chance, just over the random coins of the algorithm, the answer really is 17. It's not about the randomness of the inputs. So if you don't like 99%, you can just run the checker like 1,000 times, and if it outputs 17 like every single time, you'd have even more confidence that the answer is 17. OK, so the theorem that we basically proved is that the permanent mod of prime has a checker. OK, and we're going to use this fact to derive some cool conclusions by the end of the lecture. But also, strictly speaking, maybe what I wrote here doesn't make sense because there's this prime hanging out, which is something the checking algorithm constructs for itself. So it's not like I named a language in advance, perm, that has a checker. But just don't worry about that. In the applications, this issue will not be a problem. And in most cases, there'll be no prime or anything. It'll just we'll be talking about a language. OK, so there's something slightly funky about the statement here, but everything is fine. Here's another fact, which I will just tell you, and we'll see the proof of it later. The graph isomorphism problem has a checker, has an instance checker. And this is related to the fact, I'll mention this in a second, that this graph non-isomorphism problem has a particular kind of interactive proof. But this itself is pretty cool. So imagine what this means. If you recall, for a long time, it was not known if this problem could be solved in sub-exponential time. And then in 2016, this guy, Barak, came up with an 80-page paper that was very complicated and originally had a bug, which got fixed, which shows that it can be solved in quasi-polynomial time, which is awesome. So now imagine Barak was a true hero, and he coded it up, his algorithm. It's a very complicated algorithm, and he handed it to you, even the source code, and you're like, there's no way I can check this, right? I don't know if this is correct. It's 80 pages, group theory. But still, you were like, well, I would like to solve some graph isomorphism problems. Well, guess what? You're in luck, because graph isomorphism has a checker. So if you have some pair of graphs, G, H, that you really care about, you can use this checking algorithm on top of Barak's algorithm, such that if you plug your favorite graph G and H into Barak's algorithm, it'll either output yes. It claims they're isomorphic. And it's not hard to show with this instance checker that uses downward self-reduction that you can actually get out the isomorphism in this case. So you can actually get the isomorphism, or you can get out the claim that the algorithm is broken, has a bug. I want to say I was almost going to write Barak is bogus, but then I did not want to do that for posterity. It's totally not the case. Or it outputs no, but the point is with this instance checking algorithm put on top of it, you get actual confidence that this is true. Or you get that the algorithm has a bug. So it's always kind of good. You either get to write back to Lotzi and say well, I found a counterexample to your algorithm, so please fix it. Please fix your code. Or you get the correct answer and the confidence in it. Of course, once you get the actual isomorphism in this case, you're of course confident. But in this case, you also become confident. And as I said, the reason for this, we'll talk about it later, but it's because instance checking is closely related to interactive proofs. So roughly speaking, you have a checker for a language L if, maybe not only if, but if you have an interactive proof for membership in L with two properties. The two properties are that, first of all, the prover strategy is not too complicated. The prover himself, Merlin, if that's the prover's name, the prover only needs the power of L. So normally in interactive proofs, we just imagine that the prover is like infinitely powerful. They can like use all sorts of power to decide how to convince you or fool you. But like for example, if you remember the graph non-isomorphism protocol, basically the prover just needs the ability to solve graph isomorphism. Okay? The idea that we'll see is that like this A is like the Arthur algorithm, and C is like giving the provers answers. And like luckily in the graph non-isomorphism protocol, like basically the prover only needs to be able to solve graph isomorphism questions in order to give like the good answers. So it's enough to like cap the prover's power to that of the language. There's only one other difference between checkers and interactive proofs, which is that in checkers, it's kind of like the prover commits in advance to their strategy. So like, imagine the permanent scenario. It's like they give you a circuit that they're like, use this as my strategy, and like, I'm done. Which is different from interactive proofs. Interactive proofs, they're really interactive. So the prover can maybe change what they're going to do depending on how the conversation is going. In checkers, it's more like they like commit in advance to like, here's like a circuit that will implement my strategy. Like now I can leave. So we'll talk about, OK, I didn't write that down. I said it in words, but well, anyway, you remember it. So we're going to talk more about the relationships between interactive proofs and checkers later. Let me tell you one more fact on the topic of checkers. TQBF, the complete problem for p-space, also has an instance checker. And this is a consequence of the proof that like IP equals p-space, which we're going to review. You can kind of extract this fact from this proof. The downside is quite painful. Like it's a bit painful to extract it. You have to also prove this theorem. So, like once you know this theorem, like so it's a great thing to like have around that like a p-space complete problem has this checkability property. It's a language which is good. The nice thing about permanent is like we really could see the proof and it was like clear and it was like you used nice properties of polynomials and so forth. So that's why I really wanted to present it first. But this is also ultimately more practically useful in complexity theory. And also X-complete problems have checkers. That gets used sometimes too. But we'll just stick with permanent for now. In fact, one more theorem I'll just tell you. This is due to Ronit Rubenfeld in about 1990 in her PhD thesis. Actually, any L, any language that's downward self-reducible and randomly self-reducible has a checker. And the proof is really the same proof as the proof for the permanent. I mean, downward self-reducibility lets you reduce questions about whether X is an L to smaller questions. You can kind of then use, check those smaller questions by just asking whether you have the correct answer on lots of inputs. And you can finally get the right answer out using random self-reduction, basically as in the permanent. OK, so this is like a kind of a general situation which gives you instance checkers. And it's the reason that permanent had instance checkers. OK, so that's why we really are into permanent and sharp P, because it has this nice property. Yep.
Do we know about the SAT? Do we know that there is no checker or something? Or?
Great. Good question. We don't know whether SAT has instance checkers. I think it's believed that it doesn't. There are some theorems that try to show that subject to a standard hypothesis, like the polynomial time hierarchy doesn't collapse, that SAT does not have random self-reduction. They don't fully do it because they show that like SAT does not have random self-reductions of particular kinds where like you have further restrictions on what it means. But they're getting in the direction of showing that like SAT is not randomly self-reducible. Yeah.
So if the language is in NP, then you also get some kind of perfect soundness, right? Like it's not going to ever give you a wrong, or if it gave you a wrong answer, you can just check it. Right?
Well, it only gives you an answer. It doesn't give you a certificate.
No, I mean, if the language is in NP.
Yeah.
I see, okay. But for graph isomorphism, right?
I guess if the language has downward self-reduction, then I think you can generally upgrade the scenario to when it's like, and it's in NP, you can upgrade the scenario to like, you can extract in the yes case, not just a yes answer that you're highly confident in, but like an actual witness.
Alright, so it's an algorithm.
Yeah. Okay, this is a slightly tricky concept, instance checker. So I mean, any more questions? Okay. Great. So let me tell you a cool thing about instance checkers. I mean, it's cool just to have one, as we saw for like graph isomorphism, but they're also useful in complexity theory, in large part because of the following theorem. And the theorem's proof is almost trivial. If L has a instance checker, then the following is true. L in P/Poly implies L in MA. Okay, so this should remind you a little of Karp-Lipton, which is about SAT. You know, Karp-Lipton says that if SAT is in P/Poly, then SAT, or NP, well, it doesn't get such a great result. It gets that if SAT is in P/Poly, then the polynomial time hierarchy collapses to sigma 2, which is OK. But this is somehow better. It gets the language into MA, which is even smaller than sigma 2. Let me just remind you, I'm not sure if we proved this one, but MA is a subset of S2P, which is a subset of sigma 2P intersect pi 2P. So like MA is like a smaller class than sigma 2P. OK, can anybody say in a few words the idea behind this proof? Yes?
I mean, sorry, the circuit?
Right. Merlin sends the circuit. So I'll say it in slightly more words, but it's basically that. So like, let's assume L has an instance checker, a script A like this. And then let's further assume that L is in P/Poly. So there is a small circuit that decides L. So now we're in good shape. I mean, it's pretty much the good scenario. So on input X of length n, you know, Merlin sends, you know, the circuit for, you know, L on length n inputs. That's what it's supposed to do. In general, Merlin sends some circuit to Arthur, and Arthur is skeptical, but a randomized polynomial time algorithm. And then, you know, Arthur uses, no matter what, you know, Merlin sends, Arthur uses the instance checking algorithm. Say C on C and X. And that's a randomized polynomial time algorithm by definition. And, you know, just everything good happens, right? So if X is really in the language, then we like assume Merlin plays honestly. Merlin is honest and really sends the actual circuit, which supposedly exists for computing, deciding if X is an L. Then, you know, Arthur gets the right circuit, and you're in case 2 over there, and Arthur, you know, outputs, well, he gets the correct answer to X being an L. So Arthur, you know, decides that X is an L with probability 1. On the other hand, if X is not an L, then actually no matter what Arthur, I mean, no matter what Merlin sends, well, what could happen? I mean, Merlin could actually send the true circuit, C, that decides L. But then, you know, Arthur will just learn that X is not in the language. On the other hand, Merlin could try to cheat and beat the system by sending a circuit which does not compute the indicator of L. But then with high probability, Arthur will either get the correct answer that X is not in L and reject, or Arthur will like detect a bug and like, it's of course implicit here, but like if Arthur, gets the output that C is bogus, then Arthur rejects. So, Arthur with high probability either, correctly decides that X is not an L, or, rejects due to bogusness, Any questions about that? Okay, so that's cool. Now we can apply this fact to, all the languages that we know have checkers. Well, the main one is going to be, for this lecture, the permanent. So here's the corollary of this theorem. If P to the sharp P has polynomial sized circuits, then P to the sharp P equals MA. Actually, I just erased it, but I told you, and we'll eventually see it, that TQBF, the P-space complete language, also has a checker. And so a corollary of that is that if P-space has polynomial sized circuits, then P-space equals MA. And that's like a theorem variance on which you've seen a couple of times, but it's a better version because you collapse P-space down to an even smaller class MA than you got previously. But let's just think about the proof of this. It's like slightly not immediate because this little fact that this didn't 100% make sense because sort of this P got chosen after the permanent got fixed. But it's OK. I'll just check things for you. So if P to the sharp P is contained in P/poly, then I claim there exists a poly-sized circuit for the permanent, let's say on 0, 1 matrices. That's because every language in P to the sharp P has a polynomial sized circuit. So for the example, the language that on input a 0, 1 matrix, is 1 or 0 depending on the most significant bit of the permanent. That's in P to the sharp P, so it has a polynomial sized circuit. The language that gives you the second most significant bit is also in P to the sharp P, because you can just, in P to the sharp P, you can get the whole answer to a permanent. So you can then finally output the second most significant bit. So that has a polynomial sized circuit, and all the languages of the different bits of the permanent have polynomial sized circuits. So by gluing those all together, you can get a polynomial size, multi-output circuit that computes permanent. OK, and then that circuit exists. It computes permanent over the integers. And so then Merlin sends that circuit to Arthur. OK, and now Arthur can pick a prime. Now Arthur finds some prime P that's let's say, bigger than 2 to the n squared. Can do that with high probability in polynomial time. And then Arthur so now computing the permanent mod this big prime is the same as computing the permanents, because we only care about 0, 1 permanents. The answer to that is always at most n factorial, which is much smaller than 2 to the n squared. So if Arthur can get the correct answers to permanent mod this big prime, it's the same as him getting the correct answers to the permanent. So Arthur can use the instance checking algorithm to get correct answers to like the permanent over 0, 1 matrices. Okay, now it has to, I mean, the final thing is it has to show that like p to the sharp p is in MA, but like if you have a p to the sharp p algorithm, it's just an algorithm that like makes polynomially many queries to permanent, and Arthur can like answer them all.
Sorry, so this is like a normal Boolean circuit, right?
Yes, but well, it's like a multi-output Boolean circuit.
Okay, but they're still all polynomial size and they're polynomial many outputs, right? So there's just like a whole bunch of bits I have to keep track of. So I don't quite see why we have to worry about having large numbers appearing.
We don't, but the whole instance checker business only like worked for the problem of like permanent mod prime, not permanent over integers. This whole like prime thing, you know, I spent like some hour like figuring out the correct place to insert the prime and so forth. I think I got it right. I slightly want to say like the high level ideas like don't worry about it, but of course you should worry about it in order to get it correct. But yeah, I think I got it correct. So like technically, in some sense, like permanent over the integers doesn't have an instance checker per se, because like it's not, the whole notion of being like randomly self-reducible doesn't make sense because you don't have a notion of like a random matrix of integers. But like it does make sense mod a big prime. And
Doesn't that also make sense though if you're working over like 0, 1 entries only? You don't have to worry about huge integers popping up.
well, still like ultimately in the for example in the instance checking algorithm, right? Like at the last step you kind of become convinced that the algorithm, the circuit is working on almost all inputs, whatever that means. But then still, like, even if you want to compute a 0, 1 permanent, you have to use like random self-reduction at the end, which reduces permanent over 0, 1 entries maybe to permanent over entries between like 0 and n, or n plus 1, because of the interpolation trick. So somehow, even if you only want permanent over 0, 1, this whole instance checker thing forces you to reckon with like permanence over like larger inputs. So yeah, I think I got it right. But, yeah, it's a little like, the permanent is like so glorious and has all these like random self-reducible and downward self-reducible properties, but it does have this like one slight annoyance, which you have to like insert the prime, going mod a prime in the right location. Okay. So this is theorem. Incidentally, this theorem has the property, I don't want to dwell on this too much, but like it does not relativize. So it's another one of these theorems where like somehow the proof uses techniques that don't work if you just give everything in sight an oracle. So if you care about this fact, somehow the proof uses something that's not relativizing, and people always like to take note when that is the case. Maybe you have to even understand what it means for this to relativize, and you can think about what part of it like fails if everybody gets the same oracle. But I won't think about that. Yep.
Can you say something about the motivation for considering p to the sharp p in the first place? Like, is that the natural way to turn sharp p into a class of languages?
Yes. So basically, we do always in complexity theory like prefer to just work with like languages and stuff, but we also have this like one glorious function, permanent, that like has so many great properties. We want to like bring it into our lives. And I guess also like counting problems are natural, like counting the number of Hamiltonian cycles or perfect matchings in a graph. So yeah, that's the reason we at some point have to start talking about function problems. But like yeah, because we really at the end of the day are like more comfortable with languages, like this is the natural way to like bring it back to talking about languages. It's like all the languages that you can compute efficiently if you could compute permanent efficiently. Yep.
So when you say there's a circuit for permanent 0, 1, do we mean like any bit of permanent 0, 1?
Yeah, or I mean a multi-output circuit.
All right, you can just turn into that. Okay.
That like outputs the number in base 2.
So what version of the permanent is p to the sharp p complete? Like,
Good question. So the even Valiant shows that even computing a permanent for 0, 1 matrices is NP complete, or p to the sharp p complete.
like any bit of the permanent?
It's equivalent, but like the usual formulation is the non-decision problem of given a 0, 1 matrix, output its permanent written down. That function problem is sharp p complete. by which that sharp P completes is like under Turing reduction. So like meaning that if you could compute the permanent, P to the sharp P is just the set of all languages that you could compute in polynomial time if you could compute any sharp P problem in polynomial time, which Valiant shows is equivalent to if you could compute the 0-1 permanent in polynomial time. OK, so besides connections to derandomization, which we'll eventually get into, there's like another application of this that I quite like. It's like another one of these hilarious consequences. This one is due to Vereshchagin in, I think, 92. And it's this. The slightly zany complexity class PP does not have circuits of size n to the 100. Or more precisely, for all C, it doesn't have circuits of size n to the C. Or this is the class of like randomized algorithms, but with like potentially unbounded error. So you just have to accept with probably strictly greater than a half when you're in the language and strictly less if you're not in the language. So it's, I like these kinds of theorems because, they're like circuit lower bounds. It's like, it puts a upper bound on the complexity of a language, the uniform complexity of a language, which doesn't have, circuits of size n to the 100. There's a relationship between uniform complexity and non-uniform complexity.
Wait, you said that for all C, PV is not contained in size of n to C. It's not the same as saying it's on P/quality.
No, it's always the same. Yeah.
But you're saying there exists a language for all C. There
Right.
exists a language in PP.
Right. So for all C, like 100, there exists a language in PP. And I'm not going to lie to you, this language is probably decidable by a randomized Turing machine running in time n to the 2C, which is not in size n to the C. So like, just to remember, at first like this looks awesome, and then you're like, well, it's not so awesome because like if you mentally equated this with time n to the 100 in your head, then this would be a very non-awesome theorem because the time hierarchy theorem already tells you there's a language in P that you can decide in time n to the 100, which is not in size n to the 100. So the actual awesomeness stems from the fact that like it's even like working against non-uniform algorithms. So this is really telling us something about like the difference between, or it's like trying to get at the difference between circuits, non-uniform algorithms, and uniform algorithms. In other words, we believe actually that there's problems in P that are not in size n to the 100. But it's very hard to prove circuit lower bounds. And so like these are like sort of our best attempts at it. And these kinds of theorems, like not too large uniform complexity class, cannot be computed with small circuits, are exactly the kinds of hypotheses you need to prove derandomization results, as it turns out. So the existence of like somewhat easy to compute functions, which are hard to compute by circuits, for which there's like no small circuit whose truth table is the language here. That's what you can use to do derandomization. Basically, you take this like hard language on like log n bits, and take its truth table, which is like n bits, and you use those n bits as like a pseudorandom string for your algorithm. That's a preview of what's to come. Yeah?
Did you say believe that there's a language in P that's not in size n to the 100?
I think so, yeah.
That's like the consequence of this thing. Oh, I guess not.
No, yeah. Like I think like trying to find a clique of size 1,000 in a graph, decide if a graph has a clique of size 1,000 or 110. This is in P. I don't think it's in size n to the 100 because it's hard to sort of imagine what you're going to do other than like, even if you have non-uniformity, it's hard to imagine what you're going to do other than like try to check all the cliques, potential cliques. Okay. Let me also just ask, like, is this good? This fact about PP? Because we already know, I reminded you this at the beginning that like sigma 2p does not have circuits of size n to the 100. And even S2p, the crazy Karp-Lipton language, does not have such circuits. So like, is this even better, one might ask? Well, turns out that it is. I'm going to need to erase more to state this. I'm going to write the long version of that up there. So MA is contained in S2p. I think we never proved that, but you can try to prove that yourself. It's contained in sigma 2p, which is contained in sigma 4p, of course, which is contained in the polynomial hierarchy. which is contained in p to the pp, because this equals p to the sharp p. We proved that. This containment is Toda's theorem. Good. Kanan directly showed this does not have circuits of size n to the 100. Just diagonalize over it. The Karp-Lipton tricks show also that this one doesn't have polynomial size circuits of size n to the 100, and even this one does not have circuits of size n to the 100. Verstegen did it for pp. Where's pp in this picture? It's kind of here. So this one you proved on the test. And this one is, of course, obvious. pp is contained in p to the pp. But that's all we know. So Verstegen also shows that this guy does not have size n to the 100 circuits. It's probably worse than this result, but we don't know for sure. So, and then this is a very interesting question, which I'll say something about at some point. But let's prove this theorem. And it's this, amusing proof style. So if pp doesn't even have polynomial circuits of any size, if it's not in p/poly, then of course we're done. It's even better than what we're trying to show. Else, it does have polynomial size circuits. Oops. So any language in this class has polynomial size circuits. And this implies it's easy to see that p to the p also has polynomial size circuits. Because this algorithm just asks a bunch of pp questions, and you can answer each one with a polynomial size circuit. So you can just build that polynomial size circuit into the Cook-Levin of this algorithm. So you easily boost it up to that. But this equals p to the sharp p. This was something we did when we first talked about sharp p. You get it by binary searching. And now we have the hypothesis of this theorem. P to the sharp p is in p/poly. So therefore, p to the sharp p collapses all the way down to ma. So it's like better than Karp-Lipton. It collapses even further down. Karp-Lipton would just get you to collapse to here or here, but this gets you to collapse all the way to here. And then if you look at this picture, right, like practically, everything in this picture is between these two classes. So everything is equal. Like these guys are equal, and these guys are equal. So everything is equal. And Kanan told us that this one does not have circuits of size n to the 100, but this guy is this guy. So pp also does not have circuits of size n to the 100. So that's the end of that goofy proof. Any questions? OK, so now I'll just state in the last 2 minutes some facts for culture. Using some of the ideas in this lecture, plus some ideas we'll talk about next time when we get into the nitty-gritty of IP equals P space, and using some additional ideas on top of all those two things, Rahul Santanam in 2009 showed the following. MA, well, promise MA doesn't have circuits of size n to the 100. Okay, so we'd all really like to get that for MA, or even NP, but MA is cool. He basically gets it, except for promise MA. So this is really you're talking about instead of decision problems, promise problems. So those problems where there's some strings where the answer is yes, some strings where the answer is no, and some strings that you just don't worry about. So he shows that there is a promise problem decided by a Merlin-Arthur protocol, which cannot be decided by circuits of size n to the 100. He actually does this by showing that MA with one bit of advice is not in size n to the 100, but it's kind of technical. This is sort of the main takeaway. You should also just kind of imagine that the promise is not there. So he did it. And another thing he did in the same paper, which is nice, and it actually only uses the ideas from this lecture and not further things about IP and P space, is he shows that at least one of these two things is true. Either the thing that we really want, MA, is not in size n to the 100, or MA is not in algebraic size n to the 100. And what does that mean? It means that there is a polynomial degree family, f, which cannot be computed by n to the 100 size arithmetic circuits over z, such that the language x, f of x, for all x in the naturals is in MA. So it's like somehow MA does not have circuits, either it doesn't have circuits of normal circuits of size n to the 100, or in a sense it doesn't have arithmetic circuits of size n to the 100. And if you really want exactly MA on the left-hand side, you can get this. And using only the ideas from this lecture plus a bit more. OK, so I'll stop there and see you next week.